Usually when we talk about a medical diagnosis, there's this expectation of, like, absolute precision. It's like engineering.
Right, yeah, like
Well,
it's just a mechanical fix.
exactly. You break your arm, you get an X-ray, and the doctor just points at this jagged white line and says, well, there it is. That's the problem.
Very binary. It's broken or it's not.
But then you step into the world of teaching AI how to reason, and suddenly that X-ray machine is, it's completely useless. We're looking at this diagnostic landscape that is incredibly murky.
Oh, absolutely. It's like looking in the dark.
Right. Instead of a clear break, you're trying to figure out why this invisible digital brain just, lost its train of thought halfway through a math problem.
And honestly, trying to fix that invisible break is, it's arguably the biggest bottleneck in artificial intelligence today.
Which is exactly why we are so excited about the stack of research you sent us for this custom deep dive today.
Yeah, this one is a big deal.
It really is. For you listening, we're unpacking a highly technical, state-of-the-art foundational paper called Trajectory Refined Distillation, or TRD.
TRD, yes. It's basically a complete paradigm shift.
Because it exposes this fatal flaw in how the industry currently teaches AI to think. And it offers a brilliantly effective cure.
Yeah, because for anyone tracking the breakneck speed of large language models right now, the real magic isn't just, throwing massive data sets at a wall anymore.
Right. We've kind of tapped out the easy data, haven't we?
Exactly. We've tapped it out. The real frontier now is in post-training. It's how we teach these models to actually think, to reason step by step, and to correct themselves.
Okay, so let's unpack this. Because to understand the cure, we really need to understand the disease first.
Always a good place to start.
In your notes, you highlighted the current industry standard, which is called on-policy distillation, or OPD.
Right, OPD.
Let's give the listener a clear mental model of how this actually works before we tear it down.
Sure. So think of standard OPD as like a highly rigorous digital classroom. You have a student model, usually the smaller, cheaper AI.
Right.
And you give the student a complex problem, so it starts generating a response. But hovering right over its shoulder is a much larger, incredibly smart teacher model.
Just breathing down its neck.
Exactly. And this teacher grades the student's response step by step, literally token by token as it's being written.
Now, in the paper, they also talk a lot about something called OPSD, on-policy self-distillation.
Yes.
And they casually call it a parameter sharing variant. Let's translate that out of researcher speak. Are the teacher and the student literally sharing the same digital brain here?
Basically, yeah. In OPSD, the teacher and the student are the exact same underlying model.
Wait, really? The same model?
Yeah, the difference is just the setup. The teacher version is secretly given the answer key. It gets privileged information to help it raid the student version.
Okay, so it's like taking a test. But a clone of yourself who already memorized the answer sheet is grading your work as you write it.
That is a perfect way to put it.
On paper, this sounds like a dream scenario, right? You have this incredibly dense, real-time supervision.
It sounds ideal.
Every single word the student types is being checked against a genius-level rubric. But according to the research, this perfect grading system is actually falling completely short.
It really is. It's resulting in noisy, unhelpful, and sometimes even adversarial training signals.
Adversarial. That sounds bad.
It's terrible. It creates a massive bottleneck. The AI isn't learning how to solve the problem at all. It's just getting confused.
And to understand why it gets so confused, we have to look closely at what happens when the student model takes a wrong turn early on.
Great. The early mistakes are the killer here.
I was reading the section where they define the central villain of this whole thing, and they formalize it as prefix failure.
Yes, prefix failure. That's the core issue.
Help us visualize this. What does a prefix failure actually look like when you're training an AI?
So, it happens when a student model makes a critical reasoning error really early in its response. And in AI terms, the beginning of the response is the prefix.
Okay.
So let's say you give the AI a 10-step algebra problem. On step 2, it accidentally flips a positive sign to a negative.
Oh, a classic mistake.
Yeah, right. That's a prefix failure. And once that specific mistake is mathematically locked in, it's a dead end.
A dead end.
Yeah, because almost no logical continuation of that thought process can possibly reach the correct answer without the model actively backtracking and erasing the mistake.
Okay, that makes perfect intuitive sense to me. It sounds exactly like missing your highway exit.
Yes, great analogy.
But wait, if I miss my exit, my GPS doesn't just let me drive into the ocean. It recalculates, it reroutes me from where I am.
Right, it tells you what to do next.
So if this teacher model is so incredibly smart and it's grading every single token, why can't it just act like a GPS? Why can't it just reroute the student model token by token back to the right answer?
See, that is the exact intuition that researchers initially had. It seems like common sense,
Right.
but it's exactly why the entire OKD system breaks down. It all comes down to the mechanical constraints of how the teacher is forced to grade.
What do you mean by mechanical constraints?
Well, in standard OPD, the teacher has to provide supervision on the student's frozen, failed trajectory.
Frozen, like it can't change it.
Exactly. When the student writes that bad math in step 2, that text is locked in. The teacher isn't allowed to go back and delete it with a red pen.
Oh, wow.
The teacher is basically asked, given what the student has already written, predict the very next token.
So it's forced to build its logic on a fundamentally flawed premise.
Yes, it's stuck on the wrong road, and it's mechanically not allowed to turn the car around.
That sounds like a nightmare for the model.
It is. And because of this, the teacher's mathematical distribution, its brain, so to speak, splits.
This glitz.
Yeah, the paper refers to this as creating a bimodal mixture.
Okay, a bimodal mixture. Break that down for us.
So half of the teacher's probability mass wants to continue the wrong logic, just to maintain, grammatical and logical consistency with the flawed prefix the student already wrote.
Right, to make it flow.
Exactly. But the other half of its probability mass wants to violently pivot back toward the correct reference answer it has in its secret answer key.
Wait, probability mass. Let me just translate that for a second for the listener.
Go for it.
So you're saying the AI is literally experiencing cognitive dissonance here.
That's a really good way to put it.
One side of its brain is saying, well, to make this sentence flow naturally based on the mistake we just made, the next logical word is X. But the other half of the brain is screaming, forget the flow, just blurt out the right answer, which is why.
Yes. The teacher is literally of two minds. And this split personality in the teacher model leads directly to a total breakdown in how the student actually learns.
It creates this bizarre phenomenon known in the paper as fragmented gradients.
Fragmented gradients, exactly.
This was honestly one of the most surprising details in the source material for me, because the researchers proved mathematically that even if you have a perfect, theoretically ideal teacher model, it still becomes completely unhelpful under this prefix failure scenario.
What's fascinating here is how that degradation actually manifests in the real data.
Yeah, tell us about that.
Because the training is happening token by token on a frozen bad path, the teacher can't rewrite the earlier mistake. All it can do is repeatedly shout correction words.
Just yelling at the student.
Pretty much. The paper notes that instead of teaching actual math or logic, the teacher just starts heavily recommending tokens like, oh, wait, actually, however, or oops.
Oh my God, it's just standing at the missed highway exit screaming, turn around, over and over again while the car just speeds away.
Exactly. And because the context window keeps growing along this wrong continuation, the supervision signals delivered to the student become totally fragmented and incoherent.
So the student isn't learning a cohesive, elegant path to the right answer at all.
Not even close. It's just learning that when things start to look mathematically shaky, the teacher really, really likes the word actually.
That is hilarious, but also terrible for training. I was looking at how previous researchers tried to handle this, because obviously they knew the training was unstable.
Oh yeah, they tried to patch it.
The paper mentioned some wildly technical attempted fixes. It says things like clipping or reweighting the loss or capping the unstable high KL terms.
Yeah, it gets dense there.
Honestly, when I read high KL terms, my eyes totally glazed over a bit. What does that actually mean in plain English?
I don't blame you at all. Basically, high KL terms refers to the moments of highest disagreement or like chaos between the teacher and the student.
Okay, chaos moments.
Right. Previous researchers saw this chaos and tried to put a mathematical band-aid on it. They tried to tell the system, hey, if the teacher and student are wildly disagreeing on a specific word, just ignore that word.
Just ignore it.
Yeah, cap the penalty, filter out the noise.
But if you think about that, it's operating at completely the wrong scale. It's like telling a student who completely misunderstood a foundational algebraic equation to just, I don't know, write their incorrect steps a little more neatly.
Yeah, or the teacher just highlights one specific wrong number and ignores the rest of the garbage on the page.
It completely misses the structural problem. The failed prefix, the original sin of the math problem, is still sitting right there on the paper.
And that is the fatal flaw of those early fixes. Loss level interventions leave the failed prefix structurally intact.
The student is still operating on a flawed premise.
Exactly. So capping the penalty doesn't teach them how to actually solve the problem.
So if fixing the individual words doesn't work, we have to find a way to fix the entire sentence. We have to fix the whole path.
Right.
Which brings us to the massive paradigm shift introduced in this paper. Trajectory-refined distillation, or TRD.
This is where the whole field pivots. Because instead of grading a frozen mistake token by token with a rigid rubric, TRD zooms out.
It zooms out.
Yeah, it operates at the trajectory level.
Okay, let's walk through how TRD actually works step by step for the listener, because it's an incredibly clever mechanism.
It really is. So first, the student model makes a raw rollout. It attempts to solve the problem from start to finish.
Just like before.
Just like before. And this raw rollout might contain a prefix failure early on. Now, in standard OPD, the teacher would start shouting, actually, right at that moment of failure.
Right.
But TRD inserts a crucial intermediate step. It stops the clock.
Oh, it pauses everything.
Yes. It takes that whole raw trajectory and hands it to the teacher model, asking the teacher to explicitly rewrite and refine it.
So it gives the teacher a red pen and says, edit the whole essay, don't just grade the final sentence.
Exactly.
But here's my question with that. How does the teacher know how to edit it? What's stopping the teacher from just crossing out the whole page and writing its own answer from scratch?
And that right there is the secret sauce of TRD. The teacher uses the correct reference answer as a guiding star, but it is given a very specific prompt.
Okay, what kind of prompt?
It is instructed, like algorithmically forced, to keep its refinement as close to the student's original logic and structure as physically possible.
Oh, wow. So it honors the student's attempt.
Yes. It finds the specific computational or logical error, fixes it, but carefully preserves all the valid intermediate steps the student took before and after that error.
It stitches the logic back together.
Right, to create a single, continuous, refined trajectory. And finally, the student model is trained exclusively on this new corrected path.
Okay, I have to play devil's advocate here for a second, though.
Go for it.
Because this sounds like an incredibly complicated dance.
Yeah.
You have to generate a bad answer, stop the clock, have a massive model, carefully edit it while mimicking the student's style, and then train on that.
It is a lot of steps.
Why go through all of this? I mean, why not just have the teacher generate an absolutely perfect, genius-level answer from scratch and just force the student to copy it a million times until it learns it?
See, that is the million-dollar debate in AI training right now, and it all comes down to a concept called out of distribution.
Out of distribution.
Yeah. Let's say your student is a relatively small 1.7 billion parameter model, and your teacher is a massive multi-hundred billion parameter expert model.
Right, a huge difference in brain power.
Exactly. The teacher thinks in ways the student fundamentally cannot grasp.
Oh, it's like forcing a middle school math student to memorize a PhD thesis on quantum mechanics.
Perfect analogy.
Sure, if they study long enough, they might be able to recite the words on the page.
Yeah.
But they don't actually understand the underlying mechanics.
No, they're just parroting.
And the moment test day comes, and a question is worded even slightly differently, they completely fail.
That's exactly it. If you force the small model to blindly copy the massive model, it breaks the on-policy character of the learning.
It pushes the student into regions of probability that it just doesn't understand.
Right. So if we connect this to the bigger picture, TRD is genius because it corrects the student's own reasoning path.
It anchors the refinement to what the student is already capable of.
Exactly. TRD anchors it to the exact reasoning patterns the student has already demonstrated. It takes the highway the student was already driving on and just builds a very clear, logical off-ramp to get back to the right destination.
And because the context now grows along a naturally corrected path that the student understands, the learning actually sticks.
It sticks.
I mean, this theoretical fix is incredibly elegant. It makes perfect intuitive sense when you explain it like that.
It's beautiful in theory.
But, as we all know, in the world of generative AI, theoretical elegance doesn't always translate to actual performance.
Definitely not. Things break in practice all the time.
Right, you can have a beautiful idea that just completely falls apart when you throw it at a server farm. The real test is the benchmarks.
The math doesn't lie.
Specifically, the most punishing math tests we give to these models.
And the researchers, they did not hold back here. They stress tested this thoroughly.
What models did they use?
They used the Qwen3 model family, specifically looking at the 1.7 billion, 4 billion, and 8 billion parameter versions.
Okay, so relatively small, efficient models.
Right. And they threw them at brutal competition math benchmarks. We're talking A, HMMT, and AMO bench. alongside rigorous code generation tasks.
Let's focus on AIMObench for a second because that is notoriously difficult.
It's brutal.
For you listening, imagine the hardest high school math competition questions you can possibly think of. These are problems where you have to do a dozen complex logical steps, and if you make a single error on step 3, like calculating a denominator wrong, every single step after that is completely useless.
It is unforgiving. It is the ultimate test of sustained logical reasoning.
And the results were definitive, weren't they?
Very. TRD consistently outperformed all standard token-level distillation baselines across the board.
Wow.
On AIMObench specifically, TRD delivered a roughly 50% relative improvement for the Qwen 3 8 billion model when using that OPSD setup we talked about earlier.
A 50% relative improvement on the hardest math test.
That's huge. It's massive.
But here's where it gets really interesting. I was looking at the data broken down by what they call base difficulty buckets on AIMObench.
Oh, yes. The buckets.
This is where the researchers grouped the math questions by how hard they were for the raw base model before any of this post-training magic was applied.
Right.
And there was a specific bucket B0. It contained 23 extremely hard AIMObench problems. The base model failed every single one of these problems on all 16 out of 16 attempts. It wasn't even close.
It was a literal 0% pass rate. The model fundamentally lacked the logic paths to even conceptualize the answer.
Right. It was hitting a total brick wall. But after applying TRD, after training the model by gently course-correcting its own trajectories, the model suddenly solved 9 out of those 23 problems.
It's incredible.
It went from completely impossible 0% to solving nearly 40% of them.
Which is just a staggering statistical leap. And it proves something vital about TRD that the industry really needs to understand. It proves that TRD isn't just sharpening what the AI already knows. It isn't just making the model slightly more confident in its existing knowledge base.
So it's not just a memory trick.
No, by correcting the trajectory, TRD is fundamentally expanding the frontier of the AI's reasoning capabilities.
It's opening up entirely new highways in the digital brain, not just repaving the old ones. It's teaching the model entirely new ways to reach a solution that were previously just outside its grasp.
Exactly. But here is the twist. Making the AI dramatically smarter wasn't even the only benefit.
There's more.
TRD also radically changed how the AI speaks, and in doing so, it solved a major efficiency headache in the tech world.
Yes, the trajectory compression. This was a massive secondary benefit that emerged from the data, and it honestly feels like a cheat code. TRD makes the AI's answers dramatically shorter.
And we aren't talking about a small trim here, like just cutting a concluding paragraph. The data from the training corpus on the Qwen 3 8 billion model is wild.
Tells us the numbers.
So the median length of the raw student rollouts, the initial messy attempts before any refinement, was 7.7K tokens.
Okay, 7.7K.
After TRD refinement, the median length of those exact same answers collapsed down to just 0.88K tokens.
Wait, 0.88K. That is a 9-fold reduction in length. It collapsed by almost 9 times.
A 9-fold reduction in length while simultaneously increasing the mathematical accuracy by 50%.
That is mind-blowing. So what does this all mean for you, the listener? I mean, why should you care how many tokens an AI uses to solve a math problem behind the scenes?
It affects everything.
Well, shorter answers mean vastly faster processing, right? It means drastically cheaper compute costs.
No.
Every single token generated by an AI costs server money and energy.
Real money, yes.
But more importantly, it solves a notorious user experience problem called length inflation.
Length inflation.
Yeah.
It is a fascinating and deeply annoying quirk of modern AI.
Deeply annoying.
If you've ever used a chatbot recently, you've probably noticed it. Often, when you train an AI using standard reward methods, the model learns a very human-like bad habit.
Which is?
It learns that longer answers are usually graded higher by human evaluators. So it starts to ramble endlessly just to sound smart, even if the underlying logic is incredibly hollow.
Oh, we have all seen that.
Yeah.
You ask a relatively simple coding question or ask for a quick summary, and the AI gives you a 3-page essay full of caveats and bullet points before finally giving you the 3 lines of code you actually asked for.
Yes.
It's basically padding its answers like a high schooler trying to hit a word count.
Exactly. But TRD completely cuts through that length inflation. Because the teacher model is refining the trajectory to be as logically direct as possible, the student learns to get straight to the point.
I love that.
And in fact, the source material notes something incredible about the cost of all this. The savings in training wall clock time, simply from dealing with these much shorter 0.88K token trajectories, completely offsets the extra compute power needed to have the teacher generate the refined trajectories in the first place.
Wait, really? It literally pays for itself.
It pays for itself. You get a smarter model, a faster model, and it doesn't cost you extra time to train it.
That is the holy grail of AI development right there.
It really is. And there is one final, very subtle detail in the data regarding this compression that I think is just brilliant.
What's that?
Well, the phrase trajectory refined naturally implies that we are fixing mistakes, right? Fixing prefix failures.
Yeah, fixing the wrong terms.
But the data shows that even when the student's original raw rollout was technically correct, applying TRD still had a massive impact. It compressed those correct answers by that exact same 9 times factor.
Wow. Because even if the student technically got the right answer, they might have taken the most convoluted, agonizingly slow, mathematically messy path to get there.
Exactly. It exposed the student to alternative, significantly more concise derivations suggested by the teacher. It broadened the supervision distribution.
So it's not just error correction.
No, TRD doesn't just step in to fix errors. It actively teaches elegance. It teaches the model the most efficient, streamlined path to the truth.
Which, when you think about it, is the ultimate goal of intelligence anyway. It's not just about brute forcing an answer. It's about finding the best answer in the most elegant way possible.
Precisely.
So let's recap the journey we've been on today with the sources you provided.
It's been a ride.
We started by looking at how the industry standard of on-policy distillation acts like a strict, unyielding grader. It looks at a phrase in test paper, gets trapped by an early prefix failure, and the whole system just breaks down into fragmented, confusing gradients, where the teacher's basically just standing there yelling, wait, over and over.
Image disaster.
But by zooming out, by adopting trajectory-refined distillation, we allow the AI to learn differently. We allow its entire thought process to be gently course-corrected by a teacher who actually honors and respects the student's original logic.
Right.
And the result is an AI that is significantly smarter, pushing the boundaries of what it can conceptualize, while simultaneously being dramatically faster, cheaper to run, and far more concise.
This raises an important question, though, a question that goes way beyond servers and algorithms.
Oh, what's that?
Well, if we have mathematically proven with rigorous benchmark data that a digital brain learns vastly better when its entire underlying logic path is gently course-corrected, rather than being slapped on the wrist step by step after an initial mistake, what does that say about human learning?
Oh, wow. That is a great point.
Right. Next time you are managing an employee through a complex project or, helping a child with their math homework, ask yourself, are you acting like standard OPD?
Are you just grading the tokens?
Yeah. Are you giving them a token-level critique, correcting their spelling, or criticizing their immediate next step while leaving their fundamentally flawed premise intact? Or are you providing a trajectory-level refinement?
Looking at the big picture.
Exactly. Are you looking at their entire thought process, honoring their messy attempt, and guiding their whole path to help them actually grow?
Because whether you are a 1.7 billion parameter AI model or just a human being trying to navigate a complicated world, we all miss a highway exit sometimes.
They really do.
We all need a little help finding the right path. And sometimes we just need someone to stop yelling about the missed turn, sit down, and look at the whole map with us.
Well said.
Thank you for sending us these sources and joining us on this custom deep dive. Keep questioning the mechanisms behind the technology shaping our world, and we'll catch you on the next one.